Welcome to the online platform of KTCD College of Arts and Science. I am HoD Department of Mathematics. In this video, we discuss another important property of real number. That property is called nested interval property. Nested interval property. Before going the statement, let us see an example. Consider in equal to closed interval 0, 1. Consider in equal to closed interval 0, 1 by n for n belongs to n. Okay. Substitute the value of n. When n is equal to 1, the interval I1 equal to 0, 1 by 1. That is 1, 0, 1. When n is equal to 2, the interval is 0, 1 by 2. That is 0, 1 by 2. When n is equal to 0, n is equal to 3, we get the interval I3. It is closed interval 0, 1 by 3. Similarly, when I is equal to 4, we get the interval closed interval 0, 1 by 4. Now, what is the peculiarity of this interval? First interval is 0, 1. I1 is 0 and 1. Okay. First interval is this 0 and 1. And I2 will be the interval 0, 1 by 2. We can see that this I1 is the largest interval and I2 is contained in I1. I2 is the subset of I1. So, I1 is the largest interval and I2 is the subset of I1. I1 is the largest interval. Similarly, when we consider the next interval 0, 1 by 3, it is here 0, 0, 1 by 3. Again, the peculiarity is that I3 is this set. This is contained in I3 is contained in I2. I2 is contained in I1. So, in I4, we can see that this is I4 and I4 is contained in I3, that is contained in I2 and that is contained in I1. So, in general, we can say that In superset or equal to In plus 1 for all n belongs to n. So, this is a sequence of intervals. The peculiarity of these intervals is the intervals are nested, which is a common element in all these intervals. There is a common element exists which satisfies in all intervals 0, 1, 0, 1 by 2, 0, 1 by 3, 0, 1 by 4, 0, 1 by 5, 0, 1 by 6, 0, 1 by 7, etc. There is a common element. We can see that 0 is the common element. Hence, the intersection of these all intervals is In, intersection of n is equal to 1 to infinity of In equal to 0. Hence, a set is non-empty if the sequence is a nest. If we find a nested sequence of intervals, there exists a common element for these intervals. That property is the nested interval property. Okay. Now, look at the statement of nested interval property. What is the property states that for each n belongs to n. For each n belongs to n, assume we are given a closed interval In equal to an bn. What does the closed interval an bn denotes? Set of all x belongs to R such that an less than or equal to x, that will be less than or equal to bn. assume also that each in contains in plus 1. Then the resulting nested sequence of closed intervals is like that: I1 superset I2, superset of I3, superset of I4, etc. Has a non-empty intersection. This is the important point: non-empty intersection. So if we take a nested sequence of intervals, we get a non-empty intersection. Non-empty intersection, that is intersection of these closed intervals. We can find infinite intervals, and the intersection of these closed intervals not equal to null set. So there exists a minimum one element in this interval, this nested sequence of interval. Okay, and the figure is as follows: I1, here given that in equal to closed interval an bn. Okay, when n is equal to 1, we get the interval a1 b1. When n is equal to 2, we get the interval a2 b2. When n is equal to 3, we get the interval a3 b3, and that will be going on. And we observe that in an bn is contained in in plus 1. In plus, that is in plus 1 is contained in in. So this is the figure. Now moving to the proof. We have to find an element x between the interval a and bn. Okay, so how will you prove this? We use axiom of completeness to proving this section. What does axiom of completeness means? Every non-empty set of real numbers that is bounded above has a least upper bound or supremum. That result is used to proving the nested interval property. So, in order to show that the intersection of in is not empty, we are going to use the axiom of completeness to produce a single real number x that's satisfying x belongs to n for every n belongs to n. So, we find an x in in for every n belongs to n, and x is a real number satisfying all the property of the nested interval. Now we are given a closed interval in equal to closed interval a and bn, and assume that in contains in plus 1. That also given in the statement that in contains in plus 1. That means we get a nested sequence of intervals: I1 superset of I2, that superset of I3, superset of I4, etc. superset of in, that is superset of in plus 1, etc. Since the intervals are nested, and we have in superset or subset of I1. I1 is a subset of I1 for all n belongs to n. So that an, here the points are a1, b1, a2, b2, a3, b3, etc. an, bn, an plus 1, bn plus 1, etc. So in this figure, we can write these ans are less than or equal to b1 for all n belongs to n. Whatever may be the an, this will less than or equal to b1. Okay, now we consider the set of ans, that is a equal to set of all an such that n belongs to n. That is the left hand endpoints of the intervals. The left hand endpoints of the intervals are taken as the set a, that is a equal to set of an such that n belongs to n. We see that every bn serves as an upper bound for a. So a1 less than or equal to bn plus 1, it is also an upper bound for a2 that is less than bn, which is also an upper bound for a. Similarly, every Bn serves an upper bound for A since the intervals are nested. Since the set has an upper bound, by the axiom of completeness, we can write there exists a supremum. Let X be its supremum. So, supremum of A equal to X. So, we are writing that the supremum of all ANs are X. Now consider a particular interval in equal to closed interval a and bn. Since X is an upper bound for A, we have an less than or equal to X. Since X is an upper bound for A equal to A1, A2, etc. And the supremum of A equal to X. Since X is an upper bound for A, we can write An is less than or equal to X for all n belongs to n. That will be taken as equation number 1. Next, since each Bn is an upper bound for A, and X is the least upper bound, we have X less than or equal to Bn. Since every Bn is an upper bound for A, the intervals B1, B2, B3, etc. Bn's are the upper bound for A. So and X is the least upper bound, X is the supremum, we can write X is less than or equal to Bn. That will be taken as equation number 2. From equation 1 and 2. From equation 1 we get An less than or equal to X, and from equation 2 we get X less than or equal to Bn. So combining these two equations we get An less than or equal to X less than or equal to Bn. Hence there exists a point X between An and Bn, which means that X belongs to the interval In for every choice of n belongs to n. Hence X belongs to the intersection of the interval n is equal to 1 to infinity to In, and so the intersection is non-empty. That is the nested interval property. Okay, thank you.